welcome to the video knowledge. We take complex topics and we try to boil them down into clear, useful insights for you. Today, we're really getting into the engine room of the body, the human heart. We're going to be looking closely at the cardiovascular system's core, the body's main transport network. If you really want to grasp health, performance, even what goes wrong in heart disease, you first need to get a handle on the basic design and function of this incredible muscle pump. So our mission today is pretty straightforward. Cut through to the essential structure that makes it all tick.
Absolutely. And focusing on that structure is so important because, well, for you, listening, understanding this anatomy is the real foundation. It's what you need to understand physiology. Pathophysiology, and crucially, how clinical stuff, medicine, surgeries, how they actually work. With this system, it's like mapping the pipes before we talk about water pressure.
Okay, pipes mapped. Let's start with the sheer workload then. This thing isn't just a pump. It's like a high-performance engine built for non-stop work. The numbers are frankly kind of mind-blowing. Sources tell us the heart is punching the clock about 100,000 times every single day. Just imagine the durability needed for that. Day in, day out, for decades. And volume-wise, that work pushes roughly 5 liters of blood all the way through your body every single minute. 5 liters every 60 seconds around the clock. That level of action needs incredible efficiency.
It really does. And those huge numbers highlight this constant balancing act the body performs. This pump, it drives the whole cardiovascular system, which is doing 2 massive jobs at once, delivering the goods and taking out the trash. So on the delivery side, you've got oxygen, vital nutrients, hormones, all needing to get to every tissue, right? Brain, muscles, everywhere. But just as critical, it's also a super efficient waste disposal service. It's constantly picking up metabolic waste, mainly CO2, and sending it off to be removed. If that 5-liter per minute flow falters, that whole exchange system starts failing almost instantly.
Okay, so that's the performance benchmark? Where exactly is this powerhouse located? And what's protecting it while it's constantly moving like that? We get a good mental picture of where it sits.
Right? Context is key. The heart sits right in the thoracic cavity. Specifically, it's tucked into the mediastinum, which is the space between the lungs, kind of deep behind your breastbone, the sternum, and shielded by the ribcage. It's positioned slightly off to the left, resting right on top of the diaphragm muscle. That central protected spot gives it a solid base to generate all that force needed to push blood everywhere.
Got it. Central protected. But let's zoom in on that protection. What's actually holding and shielding this muscle that never stops moving? You mentioned layers.
Exactly. So the heart itself is enclosed in this tough double-walled bag called the pericardium. Think of it like this. There's a strong fibrous outer layer, the fibrous pericardium. And then inside that, a thinner, more delicate layer, the serous pericardium, which actually makes a little lubricating fluid. This whole sac anchors the heart, keeps it in place, and limits how much it can stretch, which is pretty important given how much it moves with each beat.
Okay, that's the outside sac. What about the heart wall itself? The actual muscle layers doing all that heavy lifting?
Right. The wall itself has 3 distinct layers, and each one's vital. On the very outside, touching the pericardium, is the epicardium. It's actually the inner layer of that serous pericardium we just mentioned. But the real powerhouse is the middle layer, the myocardium. That's the thick muscular tissue, that's the engine itself, the part that contracts. And then lining all the inside chambers is this really smooth, slick layer called the endocardium. Its job is basically to minimize FR as blood rushes through smooth passage.
That layered structure makes sense for efficiency, so the house is protected. Now, let's look inside. How does this one pump manage that constant 5-liter-a-minute flow, sending blood to the lungs and the whole body without everything getting mixed up?
Oh, this is where the clever internal design comes in. Using the 4 cardiac chambers, you've got 2 chambers up top, the atria, a right atrium, and a left atrium. They're the receiving rooms, relatively thin-walled, and then below them are the two heavy lifters, the thick-walled pumping chambers, the ventricles, the right ventricle, and the left ventricle.
Okay, let's trace the blood's journey. Where does the used blood come in and how does it get sent out? Again, full of oxygen.
Okay, so it starts with deoxygenated blood coming back from the body. It flows into the right atrium. From the right atrium, it passes through a valve, the tricuspid valve, down into the right ventricle. Then the right ventricle contracts, squeezes that blood through another valve, the pulmonary valve, and pushes it out through the pulmonary arteries towards the lungs. That's where it drops off CO2 and picks up fresh oxygen.
Got it. Lungs do their thing. Then what?
Then that newly oxygenated blood comes back from the lungs and enters the left atrium. From there, it flows through the mitral valve, sometimes people call it the bicuspid valve, into the powerhouse, the left ventricle. Now the left ventricle gives the biggest push of the whole cycle. It contracts forcefully, sending that oxygen-rich blood through the aortic valve and out into the aorta. The body's main highway, heading everywhere else.
You know, tracing that path really highlights something about the ventricle structure, doesn't it? It connects right back to the physics. The right ventricle is just pumping blood next door to the lungs, relatively low pressure. But the left ventricle, it has to pump against way more resistance to reach, say, your toes or your brain.
Exactly right. And that pressure difference, it directly dictates the anatomy. If you were to look at the heart wall, the myocardium of the left ventricle is significantly thicker and more muscular than the right ventricle's wall. It simply needs that extra muscle mass to generate the much higher force required to push blood throughout the entire systemic circuit. The rights build more for volume to the lungs, but the left is built for pressure and distance.
Okay, so you have this elegant two-circuit system, but none of it works if blood sloshes backwards. Right. Which brings us to the valves. You mentioned 4 of them. These seem like the crucial gatekeepers.
They absolutely are. They're the mechanical fail-safes. We're talking the tricuspid, pulmonary, mitral, and aortic valves.
Right.
Think of them like one-way doors. They swing open easily to let blood
flow forward, but slam shut immediately to stop any backflow.
Precisely. Their whole job is enforcing that strict unidirectional blood flow between the chambers and out into the major arteries, and preventing that backflow or regurgitation is non-negotiable for efficiency. If any one of those 4 valves isn't working right, maybe it's too stiff and narrow. That's stenosis, or it leaks. That's regurgitation. The pump's efficiency just plummets, because if a valve leaks the chamber before, it has to work much harder just to push the same amount of blood forward next time. Leads to pressure buildup, strain. It's why valve problems are so significant.
And that leads to the classic harp sounds.
That's exactly it. That familiar lub-dub sound you hear with a stethoscope. That's the sound of these valves closing in sequence. First, the mitral and tricuspid, then the aortic and pulmonary dub. Crisp closures mean healthy valves.
Okay, this next point seems really critical, especially for understanding heart problems. We've talked about all this blood passing through the chambers, but the heart muscle itself, the myocardium, beating 100,000 times a day, it needs its own constant fuel supply, right? Its own oxygen. It feels a bit weird though. The left side of the heart is full of oxygen-rich blood. Why can't the muscle just soak up oxygen from the blood already inside the chambers? Why does it need separate pipes?
That's a really insightful question. It gets right to the heart of the matter, so to speak. The simple answer is the myocardium, especially in that thick left ventricle wall, is just too dense. It works too hard, too constantly. Oxygen can't just diffuse effectively from the blood inside the chamber deeply enough into that hard-working muscle tissue. So it needs its own dedicated delivery system, the coronary circulation. This is a network of blood vessels, coronary arteries that branch off right from the start of the aorta, just past the aortic valve. These arteries run over the surface of the heart kind of like vines, sending smaller branches deep into the muscle tissue to deliver that vital oxygenated blood.
And this separate, almost secondary-looking system? This is where things get serious clinically, isn't it?
Absolutely. This is ground zero for a lot of major heart problems. The clinical significance is huge. We're mainly talking about 2 main arteries, the left coronary artery, which branches quickly to supply the all-important left ventricle in front of the heart, and the right coronary artery, which typically supplies the right side, the bottom part of the heart, and often the heart's electrical nodes. Now, because the heart muscle never rests, any blockage or even significant narrowing in these crucial coronary vessels, a condition called ischemia, rapidly starves the muscle tissue downstream of oxygen.
And that lack of oxygen leads to?
When that muscle tissue is starved of oxygen and starts to die due to lack of blood flow. That is a myocardial infarction. That's a heart attack. So knowing the exact map of these coronary arteries, where they run, what part of the heart they feed, that's absolutely fundamental for diagnosing and treating coronary artery disease, which is incredibly common.
Right, so let's pull this together. For everyone listening, we've done a deep dive into the heart's basic blueprint. Today, we covered its incredible performance stats, the layers protecting it and giving it strength, the amazing four-chamber design with its one-way valves ensuring blood flows correctly, and critically, we looked at the heart's own fuel line, the coronary circulation.
And getting that foundation is key because we started with those big numbers. 5 liters a minute, 100,000 beats a day. It's a complex, powerful machine, and we established that understanding this anatomy, well, it really is the basis for understanding treatments and interventions. So here's something to think about, a question maybe for you to consider. If this whole system relies on every single part working just right, what kind of ripple effects spread through the entire body's transport network? Affecting your brain, your kidneys, your energy levels? When just one small piece of that anatomy, say the aortic valve, or just one branch of that left coronary artery, starts to fail, think about that massive performance and how deeply just one tiny structural flaw can impact the entire engine of life. It really underscores the importance of this anatomy.
Definitely something to mull over. Use this foundation as you encounter more about health and medicine. That's all the time we have for this deep dive. We hope you found it insightful.